Okay, we're going to continue on with applications. So in the previous lesson, we looked at area under the curve. So remember, if we have a graph that, let's just do a simple one here. If we had a graph that suppose it looks like a quadratic, and if I say calculate the definite integral from 1 to 3, we figured out that that definite integral could give us the area under the curve. So in this case, the integral from 1 to 3 of x squared dx would be exactly that same thing as the area under the curve. Where we had to be careful, remember, was if there was negative sections of the graph. So if I gave you this graph and I ask you to calculate it now from 0 to 3 or something like that, now we would have a negative section and possibly a positive section as well. So in this case, if we wrote it as integral from 0 to 3 of x squared minus 1, now we're in trouble. We'd actually, if we did that, the positive and the negative areas would cancel each other out. So remember with these, what we have to do is figure out the different pieces separately. So in this case, we'd have to do the area from 0 to 1. That would be the negative area. We'd have to do absolute value of that. And then we would do the area of the positive section from 1 to 3 separately, and then add those two answers together. So that's basically the general idea of area under the curve. We also looked at area between two graphs. So if we had two graphs, we could calculate that area by doing the upper area. So in this case, the area of the straight line from say 0 to 1, and then we would subtract the area of the quadratic from 0 to 1. And that would give us that little red piece that I shaded in. So that's a quick review of area under the curve, and that's probably the most important or the most used application of integrals. But there are other ones, and that's what we're going to look at today. We're going to go through 3 different other applications that do come in handy as well. So the first one we're going to look at is the physics applications. So in our previous unit, we did the derivative of a displacement gave us velocity. The second derivative gave us acceleration. So we can do the exact same thing in reverse. So if I started with acceleration and I do the antiderivative, that would give us the velocity. But remember, antiderivatives we have to put on plus c. And that's probably going to be the biggest issue with this stuff, is you have to calculate that c value before you can do the next antiderivative. So now if we take the antiderivative of that velocity equation, whatever the c value would be, that would give us our displacement, but then we'd have plus c again, and those c's are different. Generally, those are going to represent our starting distance or our starting speed, depending on the equation we're dealing with. So let's go through a couple of examples. This first one says a car travels at a constant speed of 50. How far will it travel 6 minutes if it started 10 kilometers away from home? So the first thing we want to be careful of is watch for units. We got 50 kilometers per hour, 10 kilometers. So the first thing we want to do is divide that 6 minutes by 60, and that'll give us 1/10 of an hour. Okay, so we have to be an hour. So that's the first thing. Okay, we should be ready to go on to antiderivatives. So we know that the velocity is 50. So if we do the antiderivative of 50, that should give us our displacement. So that would be 50t plus c. So what we have to do now is, before we can solve for anything, we got to figure out what the c value is. So it says it starts 10 kilometers away. So what that's telling you is at time 0, we have a distance of 10. So we can plug the 10 in for the distance, plug 0 in for our time, and that would give us a c of 10. So now we know our velocity equation with the c value will be 50t plus 10. And that's our equation now that we can solve the question. So it says, how far will it travel in 6 minutes, or 1/10 of an hour? We plug that into our equation. So 50 times 1/10 plus 10, that would give us 5 plus 10, or a total answer of 15 kilometers. And we can see that that's our answer that I printed in the question. So with these questions, they're pretty simple. Do the antiderivative, but the issue is solve for c. And sometimes the wording can make that part a little bit tricky, but that's basically the issue you have to worry about. So this next example says a person is standing on the top of a 50 meter tall building and they throw the ball upwards at 10. So let's just kind of draw a little picture here. So at time 0, we have a distance of 50. So an important thing to figure out. So at time 0, we have a distance of 50. And let me fix that a little bit. And also at time 0, it says we threw the ball upwards at 10 meters per second. So in physics terminology, we'd call that the initial velocity. But here we'll just call it velocity is 10 meters per second going upwards. So at 0 seconds, we're starting at 50 meters above ground and we're throwing it upwards at 10. So we know from physics that it's going to go up to whatever height and then it'll fall down to the ground after that. So the only thing we know in this question besides those initial times and speeds is that the only thing that's going to pull this thing to the ground is gravity. So we know gravity is 9.81, negative 9.81. So if we do our antiderivative of that, we will get negative 9.81 t plus c. And again, we have to solve for that c value. So we're going to use our initial speed of 10 at time 0. So when we plug 0 in for time, we get a c value of 10. So we've got our velocity equation done now. Now we're ready to do the antiderivative of that. So if we take our antiderivative of that equation, that should give us our distance. So we would get t squared, we'd have to divide by 2, so that would be negative 4.905, and plus 10t, plus c once again. So now we know at time 0 our distance was 50, so we can plug that in, and that would give us a c value of 50. So we have all of our answers. Our original equation was our acceleration. We've just figured out our velocity equation, and we also know that our displacement will be 4.905 t squared plus 10t plus 50. So from here now we could, with all three of these equations, we could solve for anything. So if I asked you how fast was it going in 1 second, plug a 1 into your velocity equation and that would give you the speed. If I said what's the total height or displacement at 1 second, plug 1 second into here and that would give us our total displacement. If I asked you when will the distance be at a maximum height, well, now we go back to the last unit. Maximum distance would be when our first derivative equals 0. So we'd go back to our original equation, make it equal to 0, solve for our time, that would give us that. If I asked you how long is it going to take to hit the ground, take our distance equation, solve that one equal to 0, and that'll be our time it takes to hit the ground. So we could do whatever types of questions like we did before once we have all three equations. Our next application, this one is quite neat. It's similar to doing area under a curve, but it has a little bit of a different approach to it. So when we say the mean value of a function, what we're basically saying is what is the average y coordinate. So if I gave you, let's look at a quadratic again, if I gave you some sort of quadratic, and I say calculate the mean coordinate from x equals 0 up to x equals 3, we know that that coordinate would be at 0, 0, 0, and then at 3, 9. So what this formula is going to do is it's going to actually tell us what the average y height would be. But more importantly, if you look at the formula, the integral part looks just like area under the curve. So if I said calculate the integral from 0 to 3 of this curve, that would give us all of this area. And if we think of a rectangle, if you have the area of a rectangle and you divide by the width, that'll give you the length. And that's basically what this formula is saying. It's saying if we take that area under the curve and we divide it by the width, or you can see 1 times it by 1 over b minus a, which would give us the width. In this case, it'd be 1 divided by 3 times 0, 3 minus 0, which is 3. So 1/3 of the area should give us the length. So in this case, suppose we had an area of 30, we divide by 3, that means that length would be 10 or whatever. So basically what we're calculating is when we do the area divided by the width, that's giving us the height. So the average height or the mean value height is actually going to give us what the equivalent area would be as a rectangle. So if, instead of doing this weird curve, we could say we have a rectangle that has base 3 and a height of whatever. Let's suppose it was 4 or something in this case. That would give us our area of 12. Well, that would be the equivalent area of what's shaded. So we can think of it from an area perspective, and it helps maybe to understand the formula, but really this isn't involving area. It's just saying what is the average y height. So just like if you average your test marks, if you had 5 test marks, you'd add them all together, divide by 5. That's assuming they're weighted equally. So that would be as if you had a graph that was a straight line. If we weighed everything equally, that'd be a straight line. So if I had starting at 0 and this one was at 5, and the height was also at 5, well, the average would be exactly halfway at 2.5 if it's a straight line. But as we saw with most equations and most things in calculus, we're not dealing with straight lines. So if I had a curve that was something like this, and let's suppose it's still going from 0 to 5, well, now we have way more of the graph is down lower where it's flatter. So our average is going to be quite a bit less than 2.5. It's going to be quite lower, and let's suppose it's around 2 or something like that. Okay, so the curve is going to act as a weighted average. It's going to pull the average down. And the same thing would happen in reverse if we had a graph that did something like that, and we went from 0 to 5 again. In this case, there's way more part of the graph that's up higher, so our graph now might have an average of, say, 4 or whatever. So if you keep that in mind and you think of averages and weighted averages that way, it might help you with these questions as well. So let's do a couple examples using this formula. So the formula is do the integral of the equation between the two coordinates. So we got our definite integral from -1 to 2 with respect to x. And then the only thing we do differently is we divide it by that base, or we can times it by 1 over to take away -1. And that's it. So really it's just doing the definite integral times some sort of fraction. So in this case it would be 1/3 times x plus 1/3 x cubed. And we're going to do that from -1 to 2. So now all we do is plug in our numbers and see what happens. So we'd have 2 plus 8/3 for the 2. Then we're going to subtract it with -1, which would be -1 minus 1/3. So that should give us 1/3 of 14/3 plus 4/3, which is 18/3, which would simplify to 6. So we have 1/3 times 6, so that should give us 2. So based on this graph, whatever this graph would look like, let's just kind of analyze it. So we'd have 1 plus x squared, which is quadratic, something like that. And we're saying from -1, which would have a height of 2, up to 2, which would have a height of 5. We're saying the average between those two coordinates is going to be at 2. So you can see like this bottom part of the graph is basically counteracting that upper part. So in this case, 2 would be the exact weighted average. And here's the notes for what we just did. So you can see it's exactly what we just did. And we got an answer of 2. So we did it correctly. The next example, same sort of thing. It's just y equals x squared. So we're going to do the integral between 1 and 3 of x squared with respect to x. And our weighted part would be 1 divided by 3 minus 1. So pretty straightforward, almost the same as what we just did. So that'd be 1/2 times 1/3 x cubed between 1 and 3. Plug in our 3, that gives us 27, divided by 3 is 9. Plug in a 1, we get 1/3. 9 minus a third would be 8 and 2/3. Half of that would be 4 and 1/3. And again, if we want to look at this from a graphing perspective, we're looking at when x is 1, so from 1, 1 up to 3, 9. Right, so we're going from a height of 1 up to a height of 9, and what we've just figured out is the average is at 4 and 1/3. So halfway between those would be at 5. So you can see we're just slightly lower than the halfway point at 4 and 1/3. Okay, here's 2 more. We'll do them separately. So the first one, and it's just to practice other kinds of functions. So this first one is a radical graph. So let's look at the picture first. So that would be a graph starting at 0, 1 and curving up something like that, and it's going to end at 12.5. So we're basically going from 1 to 5 for our height, so the average should be somewhere in between. So I'm going to guess around 3 or 4, something like that. So let's do our integral. So we would get from 12 to 0, so 12 minus 0 would be the bottom of our fraction, going from 0 to 12, and we'll change our root to power of a half, so we'd have 2x plus 1 to the half, and we're going to do the integral of that. Let's fix that, it looks like a 4. So we'd have 2x plus 1. So we'll do the integral of that, so that'll give us 1/12 times. We'd raise our power to 3/2, divide by 3/2, so that'd be 2/3. And the derivative of the brackets is 2, so we also got to divide by 2. So you can see in this case the 2's would cancel out. And we should be good to go. So let's plug in our values from 0 to 12. So if we plug in a 12, we get 24, 25 to the 3/2 would be 5 cubed, which is 125. So we'd have 125 divided by 3. So let's write this out. So we'd have 1/12, and then we're going to get 125 divided by 3 for the first part. If we plug in a 0, we would get 1, so we're going to subtract 1/3. So that'd be 124 thirds divided by 12. So I'll just leave it as a fraction. That would be 124 over 36. And we could simplify that as a decimal or simplify the fraction further, but that's good enough. I think you get the point from there. Okay, letter B, same sort of thing, except it's a trig graph. So we're looking at a sine curve from 0 to 2 pi. And remember the height is at 1, the lowest height would be at -1. So just by common sense, exactly half of the graph is above, half the graph is below. So the average should be somewhere in the middle. So let's try it for the formula. So we'd have 1 over 2 pi minus 0. And we're going to do the integral from 0 to 2 pi of sine x. So that integral, remember, is negative cos x. That's on your formula sheet if you can't remember. And then we're going to plug in 2 pi and 0. So we'd have negative cosine of 2 pi, which is 1. And then we're going to subtract negative cosine of 0, which is also 1. So you can see in this case the 1's would cancel, so we get 1 over 2 pi times 0. So the average is indeed 0. So it does make sense to what we thought earlier. If we wanted to make it a little bit more interesting, maybe we would stop it at from 0 to pi and we'd look for this average height just of that first part of the curve. So the only thing that would change, let's just write it out here quickly, the only thing that would change is we'd have 1 pi instead of 2. Everything else would be the same. So now when we did our formula, we'd have 1 over pi, we'd have negative cosine of pi, which is going to be -1, so you'd have negative of -1 this time. And then we'd be subtracting -1 again. Okay, so we can see in this case, we get, instead of canceling this time, they end up being 2. So our final answer would be 2 over pi, which is about 0.68 or something like that. Which makes sense because we know halfway would be at 0.5, and because the graph is skewed a little bit heavier to the top, we should get a little bit heavier of a weighting further up the graph. So that's it for the mean value. So it's basically just a definite integral times it by the 1 over the width of the curve, and that should give you the average or the. Our last application we're going to look at today is sort of like area under the curve again, but now we're going to take that area and rotate it around. So if we take a two-dimensional object and we rotate it around the x-axis, it's going to turn into a 3D shape. So instead of calculating area under the curve, we call it a volume of revolution. We haven't done e to the x graphs yet, but you can see in this picture, e to the x would end up giving us this sort of bell shape kind of object. So let's change this. Let's make it just y equals x. So we'll get rid of the e. So that would just be a diagonal line. And if we rotated it, you could see it would turn it into a cone. Right? We would just get a triangular shaped sides, and then the front would be that circle, so we end up getting a cone. So if we think about it, the area of the base of it is a circle. So we can see the base of the circle would just be pi times our radius, which in this case is 3. So you'd have pi times r squared, or pi times 3 squared, which would be the radius of that cone at the bottom. Okay? If we went over a little slice, if we went a tiny bit over, now we'd have another smaller circle, so it'd be pi r squared again, but now our radius, instead of being 3, maybe it's at 2.5. And if we went further, now our radius is at 2, and then our radius is at 1, and so on. So as we go further and further down the line, you can see we just get smaller and smaller circles. So we'd basically be adding up all of those circles. So that's how we're getting a volume out of it. So it ends up basically being, the formula ends up being the integral of pi times our radius, which happens to be whatever our equation is. We're looking for the y coordinate of the equation. In this case, y equals x. Our radius, our height, if we were at 3, our radius was also 3, because they were equal coordinates. But if we had a different equation, like y equals x squared, now our radius at 3 would be 9. So we basically take whatever our y coordinate is, or we'll write it as f of x, and we have to square it because of the circle part of it. So the only thing that we do slightly different is, because pi doesn't really matter, we're going to move the pi to the outside of the integral sign. So we're going to do the integral of our equation squared times pi. And then again, we would just figure out where we're going to start and stop. So we'd need our definite numbers. So in this case, we would go, say, 0 to 3. And that's it. That's the formula we're going to use. So you can see here's our formula. So our volume of the integrals of the equation squared. And that's the key point. That's the part that I always seem to forget. I forget to square it if I make a mistake. So watch for that equation squared. So this next example I got, you can see it's a cylinder. So we can take this cylinder, and which is basically just a straight line. We're looking at y equals 1, which would give us that straight line. And we're going to spin that around the x-axis. So that straight line is going to turn it into a cylinder. So if we try this formula, we would have pi, and we're going to go from 0 to 1, and our equation is y equals 1, but we have to square it, which in this case doesn't matter. So we get pi times the integral of x from 0 to 1. We plug in 1, subtract the 0, we would just get a volume of pi. Let's compare that to what we already know. We know from before, cylinders are pi r squared h. So in this case, you can see in the question our radius is 1 and our height is also 1. So you can see that it actually does give us the same answer. So the volume formulas for cones and cylinders and spheres and things like that you've done before, they work great for those kind of shapes, but this integral method will now work for any kind of graph. It doesn't matter what kind of shape it is. It can be some kind of weird cone shape or a sine graph or anything, and we'll be able to calculate the volume of those shapes. So the next example I got is a circle. So if we take a circle, and you guys didn't learn circles in Math 30, so this x squared plus y squared equals 4, if we graphed it, it would be a circle with radius of 2. So it would look something kind of like that. So if we look at it and we know that our coordinates are going from 2 to -2 in each direction, we could actually try it for this calculation. So we could take the integral of our equation from -2 to 2. We have to do the integral with respect to x, and that's the only trick to this question, is we have to do it with respect to x. So we can't do implicit. What we need to do is take these starting equations and solve them so it's y equals, so in this case it'd be square root of 4 minus x squared. We don't have to worry about the negative part or the bottom part of the graph because we're rotating it anyway. The rotation will cover that. So we basically just need the 4 minus x squared and, or sorry, to the 1/2, I forgot the square root, but then we got to square the equation. So you can see the square and the square root cancels out in this case. So it actually makes it a pretty easy equation. We do the antiderivative of just 4 minus x squared with respect to x. So that would give us 4x minus 1/3 x cubed. And we go from -2 to 2, plug those values in, and we would be done. Okay. Okay, I'll stop there. I think the plugging in the numbers is pretty straightforward. Or maybe let's keep going. Let's finish it off. So we'd have pi, so we'd have 4 times 2, which is 8, minus 8/3. And then when we put in negative 2, we would get negative 8 plus 8/3. So we actually get 24, so we get 16/3 minus 16/3, so that would be 32/3 times pi. Should be our volume. And again, we could compare that if we wanted to a regular sphere formula. If you remember, volume of a sphere was 4/3 pi r cubed. So that means in this case we'd have 4/3 times pi, and our radius cubed is 2 in this case, so 2 cubed. So we'd have 8 times 4, and you can see we get the same answer, 32 pi by 3. Okay, so I'm not saying this is a better way to do the volumes compared to the regular formulas, but it at least shows us that we were able to solve them and get the same answer, which means now we can apply this to any kind of shape. I have one more example, and this one is, we're going to do it 2 different ways. We're going to take this quadratic, so let's look at the graph to start with. So I have y equals x squared, and we're going to go from 1 to 3. So we're going to start at the coordinate 1, 1, and we're going to go up to 3, 9. Oh, I need one more tick. So 3, 9 would be somewhere up there. So our quadratic graph would look, something sort of like that. Actually, that's a little too straight. Let's make it a little curvier. Right, because it would just be a regular quadratic if we're to continue this shape on. Right, it would be something like that. Okay, so there's our portion of the quadratic graph we're going to worry about. So we want to rotate this around the x-axis. So we're going to take this graph and we're going to rotate it around, so you can see that this top part would make like a circle, and the bottom part is going to make a large circle as well. So you can see the shape is going to be sort of like a sideways volcano, or kind of a bell shape, like the end of a trumpet or something like that. That's the kind of shape we're going to be solving for. So for this first part, if we do our volume calculation, we don't have a formula for this, so we'd have to do it with the integrals. So we'll have pi from 1 to 3, and our equation is x squared squared with respect to x. So we would get x to the 4th, so that antiderivative would be 1/5 x to the 5 from 1 to 3. Plug in our 3, so that gives us 3 to the 5, which is, I think it's 125 divided by 5, maybe not. So 3 to the 5 is 243, so that'd be 243 fifths, and then we'd be taking away 1/5. So our answer should be 242 pi divided by 5, and we'll do that as a decimal. So that gives us an answer of 152 approximately. So that would be that area of that cone or bell shape. So the second question, which I have on the next page, but I won't flip to it, we're going to do the exact same thing, but I'm going to change it where we're going to rotate it around the y-axis instead. So instead of rotating it that way, we're going to take this shape and we're going to rotate it sideways, so you can see it'd be more of a bowl. Right? We'd be looking for all of this volume on the top instead. But because it's the same equation, and we know the y-coordinates when x was 1, our y was 1, and when x was 3, our y was 9. So the only thing that's going to be different is we're going to go around the y-axis, so that means we need our interval to go from the y-coordinates, so 1 to 9. We need our equation, just like we did previously, we need our equation to be isolated for y instead of x, so we would rearrange this equation. That would be the same thing as x equals square root of y. So we're going to put that in as our equation and square that. And then the last part is we would do that integral with respect to y instead of x. So you can see the blue one is everything is x's, the red one now everything's in y's. Other than that, it works exactly the same. So square root of y squared would cancel, so we basically just get 1/2 y squared from 1 to 9. And if we do that calculation, 9 squared is 81 divided by 2, and we would subtract 1/2. So we get 80 pi divided by 2, which gives us an answer of about 125. So you can see the red one, the red area actually ends up being a little bit less volume. And I think the reason for it is because this base of this blue one is so big, right? That's given us a base of like 18 diameter, so that's going to be quite a large shape. So the volume of that blue one is 152, where the red one is 125. Okay? And this peak wouldn't exist because we didn't go between 0 and 1. So you can see those two shapes, totally different shapes, but fairly comparable volumes. And that's it. We're done this topic.